In the fourth and final part of the lecture, we will show how we can use kernel trick to turn a linear support vector classifier into nonlinear classifier. We will still use the example of the diagnosis of the heart failure, but we will introduce a new feature that is QRS, interval duration, and it can be extracted from ECG. We can see that mild and severe heart failure are now nonlinearly separable, but we need a nonlinear decision boundary to separate them. The dataset that is not linearly separable can be made separable by adding extra features. So here in this example, we can see linearly non-separable dataset with a single feature X. And if we add quadratic feature, so now we have the first feature, original feature on x-axis and the quadratic feature on y-axis, the dataset becomes linearly separable. So what we have done here, we replace the feature vector x by the transform feature vector phi x, where phi is nonlinear transformation. So our phi x now is x squared. To turn linear SVC to nonlinear SVC, we just need to update the decision function. So you see that here we replace the feature vector x by the transform feature vector phi x. And all the other equations that we derive for a linear SVC remain the same. So here are the new hard margin and soft margin objectives. They are exactly the same as before, except for the feature vector that has been replaced with the transform feature vector. So here is how we implement nonlinear support vector classifier in scikit-learn. We will do it as a pipeline of a feature transformation and a linear SVC. So in this case, we have a polynomial feature transformation of third degree, followed by the standard scalar to normalize the features, and then followed by linear SVC. And you can see that we've got a beautiful nonlinear boundary to separate mild and severe heart failure patients. We can also use a kernel trick to create nonlinear SVC. So to do that, we will define the dual representation A of the model parameter vector W. So this is the equation. The W, vector W, is expressed through the dual representation, the label vector, and the transform feature vector. So the dual representation elements have to be always positive or zero in this case. So we can then substitute this equation into the equation for the decision function, and we see that we obtained the kernel here, which is phi transposed x times phi xi in this case, and it's called kappa. So this is the same kernel we already seen for ridge regression, and of course Gaussian kernel is usually the kernel of choice. So the labels are predicted by thresholding the decision function as usual. So let's have a closer look at the new nonlinear decision function. This decision function is a linear combination of the kernels placed around the support vectors. This is because the dual coefficients AI are positive for the support vectors and zero for all the other samples. So here in this plot, we can see the interpretation of this equation. So we have positive samples denoted with red diamond and negative samples denoted with blue circles. And if they are circled if they are in pink circles, they are support vectors, and the kernels are shown by dashed green lines. So you see that in this case, we have only 4 support vectors, 2 positive and 2 negative, and there are 4 kernels plotted here. We have plotted these kernels multiplied by the label. So if the sample is positive, for example, like this one, the kernel will be positive as well. And if the sample is negative, like this one, the kernel is plotted negative. So we have, and they are centered around the support vectors, as you can see. We also plotted the dual representation A, but again, we multiplied it by the label so that it appears on the correct side. So we have only 4 non-zero coefficients, and you can see how these coefficients define the shape of the decision function. So we can also see that when we decrease the size of the kernel, we will have more support vectors. And in this case, the kernel is small, and actually all the samples are support vectors. And perhaps here we can see most clearly that when we have a group of negative samples, they will drag the decision function below 0. And if we have group of positive samples, they will drag the decision function above 0. So if we have a new sample that is close to the positive samples, then it will be classified as positive. And if it's close to the negative samples, it will be classified as negative. So as we already said, the dual coefficients can be either 0 or larger than 1, so positive, never negative. And if they are 0, they are outside the margin and on the correct side of the decision boundary. So that's these red diamonds here or the green triangles here. And if they are positive, then they are the support vectors, and they can be on the margin, within the margins, or on the wrong side of the decision boundary. We don't have example like that here. So how do we find the dual representation? So we can derive the hard margin and soft margin objectives for the dual representation. And here is the expression for hard margin objective for the simplicity. We don't give the soft margin objective. And we see that again, we obtain this matrix K, which has elements made out of the kernels between the pairs of the samples in the training set. So these kernels measure the similarity of the samples or their feature vectors. But actually this time we also look at the labels. So we multiply this similarity by both labels. And what this does is that if the labels are the same, then the similarity will be positive. And if they are different, the similarity will be negative, which makes perfect sense. So these dual hard and soft margin objectives can be minimized using quadratic programming solver. And here we visualize the influence of the hyperparameters C and sigma on the classification. So we can see that if we increase C, we get less smooth boundary. So for smaller C, we have smoother boundaries. And if we increase sigma, we get smoother boundary. Kernel support vector classifier is implemented in scikit-learn in object SVC. And if we set parameter kernel to RBF, which means radial basis function, it will give the Gaussian kernel. So hyperparameter gamma is a parameter of the kernel, of the Gaussian kernel, and is equal to 1/2 sigma squared. And hyperparameter C, we know already, regulates the width of the margin and smoothness of the boundary. So there is inbuilt support in SVC for multiple labels. And the multi-label classification is implemented using multiple decision functions. You will practice classification using 4 notebooks during the tutorial session. The first 3 notebooks will give you practice in implementing classification in scikit-learn, and these 3 notebooks are mandatory. And the optional notebook shows the theoretical concepts behind kernel SVC, so it's highly recommended as well. The solved notebooks are also available on Kits. So the last thing we need to do during the lecture is the quiz, which is called Kernel Support Vector Classifier. Please do not forget to submit the answers to this quiz, and this is the end of the lecture.